Good afternoon. Welcome to the next lecture in the course about, I still do not know the exact name. So I will, as usual, start by reminding what we have done already by this point. And last couple of lectures, we discussed the nonlinear sigma model, which is, I don't know how this should work. Yeah, it's red, whatever I do. Yeah, so it's a model written in terms of the matrix Q with the action that looks like this. Integral over the whole space, trace of two terms, d nabla q squared what's the correct number here? It's 2i, right? Does anybody remember the action? Plus 2i omega lambda q, and the matrix Q is a rotated matrix lambda, rotated by the rotation matrix T. T is a unitary matrix of size 2n, and the matrix Q itself belongs to what we called a symmetric space, which is U to n divided by twice un. So this is the nonlinear sigma model that we will consider for a few more lectures. And the nice thing about this model, this is the effective model that describes disordered system in terms of diffusion. Yeah, this is like a diffusion equation embedded here, and the main excitations that this action describes are diffusons or couperons, not single electrons. And these diffusons and couperons, they interact, and the interaction vertices are Hikami boxes. So the structure of this model knows almost nothing about the original Hamiltonian. The only thing it knows is the value of the diffusion constant and the fact, as we just derived it, there are no symmetries. So it's called unitary. It's a unitary case, or unitary sigma model, or unitary class sigma model. Yeah.
So we started from the operator for which we showed that in the very beginning, when we just introduced Rassmann variables,
Yeah.
we wrote action in terms of fields.
Yeah.
And introduced an operator L.
Operator L.
Which
I do not remember any.
Which in retarded and advanced sector, we show that upper left is J retarded minus 1, lower right J advanced minus 1.
Okay. Was it called L?
But nevertheless, no, it wasn't. But nevertheless, so our system, physical system, is defined at the moment when we define this operator L. And we just wrote that L is actually like psi plus random potential. So how can we understand the symmetry class looking at this Hamiltonian?
this will be later in today's lecture. You will see. So yeah, I didn't touch this topic too much. So this is unitary symmetry class. It's the simplest one, and it has the easiest derivation of the sigma model. That's why I showed you this derivation, but I didn't specify at which point the unitary class is distinguished from any other class, and it will be later today. It's still a recap of what happened in the previous lectures. So what we also did, we computed weak localization corrections. Weak, it can be localization or anti-localization. And we have seen two cases, which are called orthogonal, unitary, and symplectic. For two of these cases, for orthogonal and symplectic, we did it with diagrams, with just correction to the conductivity with a Couperon. And for the unitary case, we did it directly from the sigma model. It was on the last lecture with this fancy two-loop diagram. But in all the cases, the result is the following, that the derivative of the logarithm of sigma with respect to the logarithm of the system size, it's two-dimensional case. And then we had three different results so far. It's either minus e squared over 2 pi squared sigma. This is weak localization, negative correction. This is called orthogonal. This is the usual one did with this Couperon and things like that. Then there is a symplectic case, which is the same but with the plus sign, e squared over 2 pi squared sigma. This is symplectic. And as I explained, orthogonal class means that we have time reversal symmetry and spin symmetry. Both symmetries are present. Symplectic is when time reversal symmetry is present, but spin symmetry is broken. Spin symmetry is broken. It happens, for example, in a system with spin-orbit coupling. And finally, this unitary case that was studied on the previous lecture also has a minus sign, but it's a different thing. Here it's e to power 4, 8 pi to power 4 sigma squared. Right? And this is unitary, and unitary means no symmetries. Unitary means time reversal symmetry is broken, and spin symmetry doesn't matter actually. Can be preserved or broken, the result is the same. So there are these three cases, and there is this plot of the scaling function, d log sigma by d log L, is a function of sigma. And these three cases, they tell us that when sigma is large, it's the perturbation theory which has sigma as a large parameter. We either have a negative thing here, or a positive thing here, or a negative but smaller one. Yeah, there are these three cases. Once again, this is orthogonal. This one is symplectic. And the middle one is unitary. What I didn't tell you, and what I will not calculate explicitly, is that this simple perturbation theory can actually be taken to larger orders. You can compute further corrections that have larger power of sigma in the denominator, and you can actually do this whole thing within the sigma model, and in some sense it proves that this whole scaling theory is correct. Because as I do perturbation theory, I will construct more and more terms. but this will always be just a function of sigma. So scaling theory tells us that this derivative should be a function of sigma itself. And for those who know, who knows what a renormalization group thing is? Yeah, great. So actually what we are doing renormalization of the sigma model, and sigma model has only one parameter, which is the prefactor of this gradient term, which is nu times d, which is sigma itself. So when we do renormalization of the sigma model, we renormalize the sigma. We have some, and what stays here is called a beta function.
Like Wilsonian energy, or
like what?
like Wilsonian energy, or because like there's two, like there you either add an UV cutoff,
Yeah.
or you can do it the other way.
Yeah, I will show right now how it is done systematically. So the statement that this scaling hypothesis is actually equivalent to the statement that nonlinear sigma model is a renormalizable theory. And it can be actually proven rigorously, which I will not do. I will just show you some hint about how this renormalization is usually achieved. And yeah, so renormalization is usually the following procedure. You have some field theory and you separate the scales. You say we have fast scales and slow scales. We have fast fields and slow fields. And we integrate out fast fields such that we have some new effective action for the slow fields. And this is the renormalized action. So what we do, we write this Q matrix in the following way. It's T inverse lambda T. So we write T inverse slow, T inverse fast, lambda, T fast, T slow. So we take advantage of the fact that the matrix T belongs to a group, which means the product of two such matrices is also an element of the same group. And we say the whole matrix T, this is the whole matrix T, can be written as a product of this fast matrix and the slow matrix. Then, once we do such a separation, we take the inner part, this one, with the fast matrices and lambda, and we say what's written here is T inverse slow, and then it's a Q matrix. It looks exactly like a Q matrix, but it contains only fast degrees of freedom, Q fast, and then another T slow outside. So the full Q matrix, which contains both slow and fast degrees of freedom, is separated into a matrix with only fast degrees of freedom and this slow T on two sides. And then we say that we have some action, or we have a partition function, the exponent of the action of Q, and it's written like this, T inverse slow, Q fast, T slow. This is the usual thing. And we do perturbation theory only in the fast degrees of freedom. So we use any parameterizations from those that were discussed last time to write it as the exponent of minus S T slow, lambda, and then f of w.
What says fast and slow?
I will say it right now. Fast and slow in real space, something that changes rapidly, which corresponds to larger values of momentum, and something which changes slower and corresponds to smaller values of momentum. So this separation is usually done in momentum representation. You have a field like W or B or whatever, which depends on point in space. You do Fourier transform, it depends on momentum, and then you say that whatever corresponds to momentum larger than some threshold is the fast field, and whatever corresponds to momentum slower than this threshold are slow fields. Yeah, and the goal is to integrate out these fast degrees of freedom. So you say the integral over W with some probably Jacobian, depending on which parameterization you choose. Then if I do it like this, the left-hand side is no longer valid. So I should erase it. And this integral gives you something which is the new action, the renormalized action. This was the old action. This is the new action, new or slow action that should, in principle, depend only on the slow Q matrix, should depend on T inverse slow, lambda T slow. So if you take this thing and expand in this fast variable, in this fast W to any order, to third, fourth, whatever order, do this integration. If you can then combine the result in this form, you prove that the theory is renormalizable, and you find what is the effective slow action for this slow part of the field.
So basically, like, you don't get any new irrelevant, you don't get new relevant terms.
Yeah. And even worse than that, even if you do not get any irrelevant terms, you also should show that the new action depends not on matrix T itself, but only on this combination. This is the most important thing, and actually it can be proven without any calculation, just by considering the gauge symmetry of this theory. I have mentioned this, well, more or less like this. Let me put it like this. If you take this T slow, this slow field, and multiply it with the matrix K from the left that commutes with lambda, on the left-hand side, nothing should change. On the right-hand side, something will change, but you can then attribute this Q matrix to W. You can include it in W, redefine this fast field, and using the symmetry of the action, you can show that this integral will not change. So if you can show that this integral does not depend on such a matrix K, you can do a conclusion, you can draw a conclusion that the result of integration should depend only on this combination, because this combination also does not depend on K. Yeah, and actually the question about relevance, we have the action which has gradient to power 2, and all higher powers of gradient will be irrelevant. That's why it is highly unlikely that we generate any new terms. The only question is whether we can generate a term that combines in the same object here. Sorry?
If they will have the same structure.
Yeah. Yeah.
So I understand we'll separate fast and slow variables, but how this equation comes in?
You mean this equation?
Yeah.
This is a definition of the left-hand side. You calculate this integral, and whatever you get defines you the new action.
I mean, to one loop is probably.
What is J then?
J is the Jacobian of the parameterization f of W. We discussed it on the last lecture. For some parameterizations, it's absent.
I've seen proofs in the cases where you do it for occupational theory, but can you prove this like to all workers?
Yes, actually, that's the point. We did this calculation last time in a perturbation theory in this unitary model to get this result, but we didn't prove the renormalization. What we did actually, we find the correction to the quadratic term. Actually, there is also a quartic term in that same action that also contains the diffusion constant. So in principle, we should have also calculated another diagram which gives the correction to the quartic term, and we should show that both diffusion constants get the same correction, and the whole action preserves its structure. We didn't do this, and we will not do this. But actually, it's not that hard. Instead, I just claim this without any proof. But I'm telling you that this can be proven without any explicit calculation, just by invoking the symmetry, the gauge symmetry, this symmetry that T, once you change T multiplying with this matrix K, nothing should change. This was the symmetry of the original action, and it should be retained, it should remain the symmetry of the action for slow fields. And from this requirement, you more or less can prove that if you calculate correction to the leading term in the W expansion, all other terms will get the same correction automatically just to maintain the symmetry. So once again, this is not a proof, it's just a statement. And whoever does not believe it can check it perturbatively to any order. It's quite easy. I mean, not very easy, but it's doable. I did this once, not to all orders, to a few of them. It's just a statement. Sigma model is a well-defined renormalizable theory which to some extent proves the scaling hypothesis. So the scaling hypothesis just tells us, well, I'm not sure even which statement is the primary here. So renormalizability of sigma model is equivalent to the scaling hypothesis. And yeah,
What is the mathematical structure of W?
of W. I can remind you, it's this matrix we had last time, B minus B dagger. So it's a matrix that anti-commutes with lambda and which is anti-Hermitian. Last time we did all the same thing without the slow fields on both sides. So we take the full Q matrix and we parameterize it like lambda times f of W. This is another way to do renormalization. You can say that W is this, and then you have fast B and slow B. So B is the sum of two, fast plus slow. And then you do expansion in the fast part, and you retain the slow part, and you get the action for the slow part in the end. It's the other way of doing this, but if you separate variables like this into T matrices, it allows you to use the symmetry to prove the renormalizability. But the result is the same. You can do calculation in both ways. So once again, sigma model is an effective field theory. The only parameter, the coupling constant of this model, is conductivity itself, is the product nu times d, and it's a nice renormalizable theory, which means that this parameter sigma obeys some RG equation, which is d log sigma by d log L is a beta function of sigma. And what we did, we computed this beta function to the leading order in the limit of large sigma, so somewhere here. But if you do the calculation to higher orders, you, at least in theory, can recover the whole function.
So this is the correction, but specifically this problem.
Yeah, this is a correction that works in the limit sigma.
Yeah, but like it's
Large.
only sensible to use in 2 dimensions, right?
Yeah.
Because
So
for 1 or 3.
2 dimension is the critical dimension for the sigma model.
As I remember, usually a renormalization group works in case when we have logarithmically divergent integrals. Yeah, but in this case we have them just into the
Yeah, yeah.
So is this beta hypothesis correct in 1D and 3D?
It's less obvious, let me put it this way. In 2D, it's more rigorous. In 1 and 3D, I would say it is still correct in the limit of large sigma. When you have a good metal with some small corrections, you will have corrections not to 0, but to a constant. It is still possible, but in general, it's
The only problem is like
not that obvious.
if you're in 3D, I think the term itself is already irrelevant.
Yeah, exactly.
So in 1D though it should work.
Yeah, but on the other hand, in 1D, it's too much relevant in the sense that everything is localized and you don't have any metals in 1D, not even a chance of having them. But yeah, so the statement is the following. Let's concentrate on 2D. In 2 dimensions, there is a very nice theory that can be nicely renormalized. It has only one coupling constant, and it has the RG equation, and that plot is just the plot of the beta function. Again, this is not, even in 2D, this is not a rigorous proof, it's just a proof, a perturbative proof, saying that if we do expansion in the limit of large sigma to any order, we will get a renormalizable thing. It doesn't mean not any function can be restored by its expansion in a certain limit.
So, can you repeat again, like renormalization is introduced when something divergent, and in our case, what is divergent?
I didn't say something divergent.
That's the other RG.
Andrei asked about some logarithmic divergence.
Yeah, Andrei meant that in 2 dimensions, 2 is the critical dimension for this theory, which means that the diagrams diverge logarithmically. It is this logarithm that we had in the weak localization correction, which then went to this denominator d log a, this logarithmic divergence. That's
Just to be at two cutoffs. One cutoff is the L and the other is like another one which you introduced to define the theory.
yeah, and also the very fact that this sigma model exists and it's renormalizable, it not only proves the scaling hypothesis to some extent, it also proves the universality. For example, this sigma model that we have as a unitary class, it was derived for any Hamiltonian. We didn't specify any particular dispersion relation or any particular value of tau of the disorder parameter. It's all hidden inside the diffusion constant. And we get just the single, for unitary case, just the single beta function that should, in principle, apply to all systems with broken time reversal symmetry. And also we have shown the limits of this universality, namely, for broken time reversal symmetry, we have one beta function. For systems with time reversal symmetry, we have two other beta functions, which I did not derive, of course. And in a sense, you can do this thing in the inverse direction. You can say, let's write down all possible sigma models, and the number of them will be the number of possibilities for this beta function.
The only thing that bugs me a bit is like, what if you add just, for example, if you add to your system a very small amount of magnetic impurities?
Oh, that's easy. That's an easy question. You can break the symmetry slightly if you add a small amount. This situation corresponds to a crossover between two symmetry classes, which means on some length scales, on the relatively short length scales, you are in the orthogonal class. On the longer scales, which is longer than this time reversal break in length, your model will become a unitary class model.
Okay, so it's not like a sudden transition.
No, it's a crossover that happens in the on different length scales. So you have a certain window of lengths with one type of symmetry and the rest with the lower symmetry. So once again, Nonlinear sigma model is an effective theory that operates in terms of diffusons and couperons, which knows only about the symmetry. And what we will do now, we will list all possible symmetries, and we will find all possible types of the sigma models. So that
Sorry, when you refer to some theory as like a sigma model,
yeah,
what do you mean?
a model that describes diffusons and couperons
Okay, so whatever
and their
has the
interaction.
letter,
Whatever what?
whatever theory has the letter, we'll call it
All
sigma.
types of the letters, yeah, the theory that operates in terms of this effective two-particle, you will see. Just a moment.
Superconductivity is a sigma model?
Sorry?
Superconductivity is a sigma
No,
model?
superconductivity is a particular phenomenon.
Not a sigma model.
No, it's not a model at all.
You could say it is if you fix the absolute value of psi.
It fits the definition.
To which definition?
It deals with couperons.
No. Cooper pair is not a couperon. Cooper pair is a bound state of two electrons, which do interact. I study only non-interacting
Usually you
systems.
want more than one dimension to have a sigma model.
Well,
Superconductivity would be like a 1D sigma model, which is not really a manifold. It's like a line.
Superconductivity is three-dimension.
No,
Okay.
it's not a target manifold.
so
Okay.
the new topic is called symmetry classification. So I will now explain how this orthogonal, symplectic, and unitary appear, what is the difference between them, and what are other options. So it's symmetry classification of disordered systems. Symmetry classification of disorder. Some facts from this symmetry classification we have already seen. So there are in total 3 possible symmetries. In the whole world, there are only 3 symmetries. And symmetry number 1 is called time reversal. Time reversal symmetry, or we will denote it just by a letter T, not the matrix T, just the letter T. Yeah, it's the symmetry of the Hamiltonian. And time reversal symmetry is the following statement. If your Hamiltonian, after you apply complex conjugation, Hamiltonian is just a huge matrix with numbers. With complex numbers, you can apply complex conjugation. Your Hamiltonian should be equal to itself complex conjugated. That's time reversal symmetry. Hamiltonian is a real matrix instead of complex Hermitian matrix. It's a real symmetric matrix. This is the simplest case. There is a more intricate case when you apply complex conjugation and your Hamiltonian is not exactly the same, but it is the same up to a certain unitary rotation. U is a fixed matrix. It's just a given matrix. Hamiltonian is random, it's disordered, you have many realizations. For all realizations, there should be one single matrix. U, for example, it can be a unit matrix, then it's just H equals H star. So this is the most general form of time reversal symmetry. Inside this most general form of time reversal symmetry, you can now do something to it. You can say, let's change the basis. We can write this Hamiltonian matrix in, for example, in real space, or in momentum space, or in some other strange basis. Any change of basis is the rotation of this matrix H, some unitary rotation. And the conjugate matrix will be also rotated, which means that if you know this matrix U in one basis, you can go to a different basis and you can change this matrix U. It is basis dependent. U is basis dependent. But there are certain things about this matrix. Sorry, it should be dependent. I forgot my English. For example, if possible, I will choose a basis in which U is a unit matrix. Then it's the simplest identity I can have. But not all matrices can be brought to a unit matrix. There are actually two cases in total. What this matrix U can be. You can ask yourself what happens if you compute this product. Again, I'm doing this without derivation, but it's quite easy actually. So this product U times U star by a proper selection of the basis can be brought to either +1 or -1. Or, no, sorry, that's wrong. This product U times U star in any basis should be either +1 or -1. It's like you apply the time reversal operation not to the Hamiltonian but to your wave function, and then let's do this. Actually, this is simple. Let's do it. So this is the symmetry of the Hamiltonian, and this is your wave function which obeys Schrödinger equation, some eigenfunction of this Hamiltonian. We can take the complex conjugate of this identity, right? And then we can insert here between these two matrices, we can insert U inverse. And then we can take this whole identity and multiply it with U inverse from the left. So what we get is U inverse H star U inverse psi star equals E U inverse psi star. I didn't do anything. I mean, it's just the identical transformation. But I did it such that here in the middle, I have something that should be equal to the Hamiltonian itself. So this is just, again, the same Hamiltonian. So I have just proven that whenever psi is the eigenvector, so is U inverse psi star. And this is how the time reversal acts on the wave vector. You have a wave vector, you reverse time, the Hamiltonian goes back to itself, the eigenvector changes. So time reversal operation, in a sense, time reversal operation is K times U inverse in my notations. K is the complex conjugation. So it's something, it's a linear operator which acts to the right. First it conjugates, then it multiplies with U inverse. This is the result. So T times psi equals this. And now I ask what happens if you reverse time twice? What happens if you apply T square psi? What is this? That's easy. You say U inverse K times psi, right? And you get U inverse U star inverse psi. So this complex conjugation, both will bring psi back to its original form, and only this one will act on U inverse and produce this thing. And then it's just a physical, if you like, intuition or knowledge that if you reverse time twice, you should go back to where you started, which means that this should be a matrix which is 1 up to arbitrary phase. Well, because the phase of the wave function is not observable, it can change, it's just a gauge thing. And then it turns out that this phase cannot be anything, it can be either +1 or -1, so either phase 0 or phase pi. It just follows from the fact that it's a unitary matrix. So if you have a unitary matrix and you know that this product is absolute value 1, you can easily see that these are only two options. So this was a side note. It's not a part of our lecture. Sorry? Only the
The statement for time universal symmetry in terms of T looks like H equals to T, TH.
oh no, T inverse HT.
T inverse HT.
So U is
THT inverse. That
Yes.
no, not original.
Yeah, so this is T. Look, this is, oh, sorry, this is T. This is time inversion operation. And again, I already did it. I can write it again. If you have a Hamiltonian and some eigenvector, you can apply this time reversal operation like this: T inverse T psi, and then you apply T from the left equals to E T psi. So this T psi is the time inversion which acted on your vector, and this is time reversal that acted on your Hamiltonian. And then if it's U inverse K, let's write it, U inverse K times H, and the inverse will be KU. Right? So this thing in the middle is just H star, and we go back to the original form. So this is this is not actually a part of the lecture I wanted to give. I just wanted to make this statement that there are two options for this matrix U. Either U times U star is +1 or -1, and these are exactly the two cases that are called orthogonal and symplectic. This is orthogonal. This one is symplectic. And
So again, the +1 and -1, you mean that this is matrix +1? Or
yeah, unit matrix or minus unit matrix. And actually by choosing a proper basis, U is basis dependent, by choosing a proper basis, in the orthogonal case, you can always make matrix U be in a unit matrix. So you can choose a basis in which H just equals H star. And for a symplectic case, you can always choose a basis in which, so you can choose a basis when U is just the unit matrix. And in symplectic case, you can always choose a basis where U is this matrix, 1 minus 1. Off diagonal times it, well, it's a big 1 and a big minus 1. And this is what usually happens with spin when you have spin-orbit coupling. Time reversal involves the matrix I sigma y, so this is I sigma y. You can, in a symplectic case, you can always bring U to the form which looks like spin. And in orthogonal case, you can always bring U to the form which is just unity, which is nothing. And also, if you take the whole operation T and square it, this is the same. You get either +1 or -1. In the same cases, this is orthogonal and this is symplectic. So once again, any time reversal symmetry has this form with some fixed matrix U, and then by choosing a proper basis, this matrix U can be either brought to a unit matrix, then this is called orthogonal case, or it can be brought to this form, then it's called a symplectic case, or you can do it differently. You can take this time reversal operation, square it, and you either get +1 or -1 immediately, which tells you whether this is orthogonal or symplectic without choosing any proper basis. This should work in any basis.
Is there any example of simple single particle Hamiltonian in which we can calculate some observable and see what is the difference between like orthogonal and symplectic class?
Oh, that's very easy. So an example of orthogonal class, Hamiltonian has the following form: p squared over 2m plus v of x. This is orthogonal. It's a real object. I mean, it's just a real number. So if you apply complex conjugation, it's the same. The example of symplectic, well, let's do the same thing. P squared over 2m plus v of x, and we add something that is called spin orbit coupling. So we need a spin operator, and we can do it like this. For example, px times sx plus py times sy plus pz times sz with some coefficient lambda. This is symplectic. And I can prove it. That's easy. H star equals all the same thing, p squared over 2m plus v plus lambda minus px sx plus py sy minus pz sz. Why is that? Because just as a side note, the complex conjugation of momentum is minus momentum, because momentum is minus I derivative. This I inside means that complex conjugation in real space representation changes sign. And these are Pauli matrices sigma x, y, z, and the matrix sigma y contains I minus I, so complex conjugation changes sign. So in this term, both P and S change sign, and in these two terms, only P changes sign, but not S. That's why I have minus. Now, if you take this H star and multiply it with Sy from both sides, guess what? Sy anti-commutes with Sx and Sz. So it will flip these two signs once again, and you will get back your original Hamiltonian.
And this is exactly the Sy which is written.
Yeah. You can add here ISY, and here ISY inverse is the same thing. Yeah, so it's just the symplectic class in its form, like here. Okay, so this was about time reversal symmetry, and I just tried to show you that the time reversal symmetry is either absent, we have system without time reversal symmetry, or whenever it is present, there are two types of time reversal symmetry, and then all other cases are just related by the change of basis. So you can always, by properly choosing the basis, you can always bring the system to one of these two cases. So, number 2, the symmetry number 2 is called a charge conjugation symmetry.
Sorry.
Yeah.
Can I ask about the crossover in your example?
Crossover.
Yeah, if we will limit lambda to 0, how this eigenvalue minus 1 will go to 1?
If you put lambda to 0, I will answer to this a bit later, okay? Charge conjugation is another type of symmetry. It's very similar to what we just see. Charge conjugation, or we will for short call it C symmetry, is the following statement, that the Hamiltonian equals the conjugate Hamiltonian up to a unitary rotation, but with a minus sign. So when you apply complex conjugation to the Hamiltonian changes sign, maybe up to some unitary rotation. So it's almost the same as time reversal, just this minus sign is the difference. And all the same thing is true. U depends on the choice of basis, and there are two cases. Exactly like there. U times U star is either plus 1 or minus 1. And C squared, this operation applied twice, also is either plus 1 or minus 1. These cases do not have names. They are not orthogonal or symplectic. It's just two cases for the charge conjugation symmetry. And the usual situation when you encounter charge conjugation symmetry is in superconductivity. So the Bogoliubov Hamiltonian for superconductors always has such a symmetry. Example. So it's an example. If you have a Bogoliubov-de Gennes Hamiltonian, it's a matrix like this: H minus H star, delta delta star. You can easily check that this Hamiltonian will flip sign if you apply conjugation and some unitary rotation.
So first we either have time reversal symmetry, either charge conjugation.
Or both.
Okay. That C is unitary complex conjugation with minus. Unitary
No, C is the same as T is unitary and complex conjugation.
C is the same operator as T.
With a different matrix U.
Okay.
Example. So this was an example. What does this charge conjugation symmetry actually tell us? If you have a state H psi equals E psi, if you have some eigenstate of your Hamiltonian, and you apply this charge conjugation symmetry, you do it like this, yeah? U inverse H star, U inverse psi star equals energy U inverse psi star. I did exactly what I did with time reversal, just no distinction at all. But now this thing is not H, it's minus H. This minus is the distinction. So if you have charge conjugation symmetry and psi is the eigenstate with the eigenvalue E, then U inverse psi star is also an eigenstate with the eigenvalue minus E. That's the difference. In a Hamiltonian with charge conjugation symmetry, the spectrum is always mirror symmetric. Whenever you have positive eigenvalue, you have the similar negative eigenvalue.
So it's the same as particle symmetry.
Yes, it's just the same, the other word to say particle whole synchrotron. Particles become whole when you conjugate their charge.
I have one question.
Yep.
So this Bogoliubov Dejean Hamiltonian, it has the c squared is equal to +1 or -1?
This one that I shown here is +1, I believe.
And what is an example of -1?
Oh, that's a bit trickier. You will need to add here the spin orbit coupling. So you increase the matrix twice more. It has both spin and this particle hole sectors. Then you can.
Sometimes you also get redundant solutions.
That's also possible. We can check this. Actually, let's do a simple exercise. H star equals, yeah, this is my Bogoliubov Hamiltonian, equals H star minus H delta star delta. I would like to apply some unitary rotation that will bring it back to this form or to minus this form. So what should I do? I should interchange H and H star. I should interchange delta and delta star. That's interesting.
H and delta matrices, because Hamiltonian should be Hermitian.
Sorry? Sorry?
Are delta and H matrices?
No, delta is a number, H is a matrix. That's a. Actually, that. Okay, so sorry. Yeah, delta usually is a number and H is usually a matrix.
But delta can be a matrix.
Hmm?
Delta can be a matrix, right?
In principle, yes, can be a matrix as well. So in the simplest case, I mean, for usual superconductor, it's just a number. So I would like to have H and H star as Y as, so the sum H minus H star already changed the sign. Sigma z should change sigma z. Yeah, so my answer is the following. H equals minus H, oh, sorry, equals minus, and then sigma x, yeah, I was wrong. 1 minus 1 times H star times 1 minus 1. Can anybody prove that this is correct? I mean, you take this matrix, you multiply it from the left and from the right by these two.
What's the square? Yeah, okay. So this matrix anti-commutes with H, and then
Let's do it. I mean, they're simple matrices, right? H star, delta star, delta minus H times 1 minus 1 from the left and times 1 minus 1 from the right equals 1 minus 1. First row by the first column minus delta star. First row by the second column H star. Second row by the first column minus delta. First row, sorry, plus.
But actually,
Plus H, sorry, I will first finish this, then you will ask the question, then delta here. Yeah?
if one of them are U, so the second one should be minus U to the power minus 1.
This we will discuss
Okay.
in a minute.
You can,
First by first h, first by second delta, minus delta star. So something is wrong. Minus h star. I got back the same Hamiltonian. This is crazy. This
minus, there is overall minus.
can you say the full sentence?
No. I mean, I thought that I understood what I misunderstood.
H, once again, I have 1 minus 1, 1 minus 1.
Yeah, so yeah,
That's not the
Can-
inverse.
Can anybody do the calculation?
so
In,
Yeah, we got
Can
the
I-
same.
just I think that this is a U.
sorry, this was not my question. My question is this correct or not?
It looks correct. And
Okay, great. Then,
Why do you need
did you check it?
to see the problem?
This is plus because you're using the inverse.
yeah, so it actually was my statement.
Great. So your statement was a different sign, not that this is you.
Yeah, I just wanted to say that.
Thank you. Yeah, exactly. So, yeah, we have just proven that Bogoliubov Hamiltonian does have a C symmetry, but I was wrong. C squared actually is minus 1, not plus 1. We should immediately erase this thing before anybody else saw it. Okay, well, never mind. So, there is a third situation, third type of symmetry, which is called chiral symmetry. Chiral symmetry. And chiral symmetry has a usual notation. It's called CT, because it's a product of charge conjugation and time reversal. Chiral symmetry has the following form. The Hamiltonian equals to itself with a minus sign up to a unitary rotation. And in the case of chiral symmetry, there is no distinction whether it squares to 1 or to minus 1. It's always squares to plus 1. There are no other options. And U is again basis dependent, and if you choose a proper basis, you can bring this matrix U to, guess what? To the unit matrix, right? And then H equals minus H is 0, problem solved. No, you cannot bring U to a unit matrix because this would be very strange restriction. But you can bring it in a proper basis in a proper basis. You can make the matrix U diagonal with 1 and minus 1 on the diagonal. So you can diagonalize it, but you cannot make it completely unity. So that's it. There are no other symmetries. And actually, it's quite easy to prove. For example, imagine your system, as you just asked, has two symmetries, two time reversal symmetries. two time reversal symmetries, T1 and T2. T1 and T2, and they act like this. The Hamiltonian equals up to a unitary rotation complex conjugation. It's U1, and it is also equal up to some other unitary rotation for the same thing. Just imagine you have two different time reversal symmetries. You have more than one of them. Then, just by comparing these two things, you can easily prove that the Hamiltonian commutes with some matrix. There is a certain matrix that commutes with the Hamiltonian. In this case, it will be probably a matrix like U1, U2 inverse.
One step back.
Where?
Yeah.
Sufficient memory. This one?
No, the last one, on the right. Yeah. I mean, it seems that it is just one.
Delete. Can I delete this one? And this one as well. What should I press to close this?
Left.
Yeah.
Yeah, so if you understand correctly, that CT operator is just some unitary operator.
It's a unitary operator
Just
that
some.
changes the sign of Hamiltonian. So in a sense,
I is E equals to U.
no. Or, well, okay, yeah, you can say that it's unitary, but it does not commute with the Hamiltonian. It changes, it anti-commutes with the Hamiltonian.
Yes.
Yeah. Let me finish this thing. So, if you have two different time reversal symmetries in a system, from combination of them, you can find a certain matrix that commutes with the Hamiltonian. And this certain matrix depends on the basis. So I can choose a basis in which this nice matrix is diagonal. And if a certain diagonal matrix commutes with the Hamiltonian, it means that each eigenvalue of this matrix defines a subspace defines a certain subspace, and the Hamiltonian does not couple these subspaces. Which also means that we can break the Hamiltonian into independent parts, each acting within a certain subspace where this matrix is just a number, and inside this small part you have no time reversal symmetry. Yeah.
What do you mean by two time reversal symmetries? It's like changing arrow of time from one.
No, wait. The real time reversal symmetry, if you take the real time and reverse it, is only one thing. But earlier I have a definition. Now it doesn't move anymore. So time reversal symmetry is actually any symmetry. This thing. Any symmetry of this form when the Hamiltonian equals its own complex conjugate up to a unitary rotation. So if you can have a Hamiltonian that, let me give you an example. Now I have to scroll it all the way back. I can give an example. So it's not real time inversion, it's now a purely mathematical notion. Example, exactly like Andrei was asking, what if I take the situation with the spin orbit coupling with the Hamiltonian that has lambda, with the Hamiltonian that is p squared over 2m plus v plus lambda p dot s, and put lambda to 0. is it orthogonal or symplectic? So on one hand, there is a symmetry. H star multiplied by Sy from both sides equals H. It's symplectic. On the other hand, if you say lambda equals 0, there is another time reversal symmetry. H just equals H star. By comparing these two things, I conclude that H commutes with Sy. Just commutes. So I can go to a basis where Sy becomes Sz. I just rotate y to z. And I have Sz is either +1 or -1. So I have two subspaces, spin up and spin down. And in each of these subspaces, my Hamiltonian, oh, actually we're blocked. Shall we?
Ja sam zaprla da se ne sliši se
Oh,
samo.
okay. So in each of these subspaces, we will have probably only one time reversal symmetry. I have no idea what you're saying.
Close the door so you will not hear the vacuum.
Oh, okay. Very good. So, does it answer your question?
Okay, so
When lambda equals 0, we have two copies of our Hamiltonian for spin up and spin down, which are completely identical. And in a sense, we can throw away spin as a degree of freedom and look only on spin up part. And this spin up part, it still has a time reversal symmetry, which is of this type, but no any other.
okay, good. So we have like two different types of symmetries, but in different spaces.
No. Whenever you have more than one symmetry of the same type,
Yeah.
it will break your system into subspaces in which you will have fewer symmetries inside each of them.
So the question was orthogonal symplectic, so you say that...
Orthogonal. The answer is orthogonal. Orthogonal, but with extra double degeneracy in spin space. So each eigenstate is doubly degenerate in spin. If you disregard this degeneracy and look only on the values, it's like a usual orthogonal system with the symmetry with only this. So if lambda is 0, you have this Hamiltonian, it's just a real matrix, there are no other symmetries. But it's multiplied. In a sense, look, the problem is that it's not shown here, but this whole part is actually multiplied by S0, by unit matrix in spin space. So if you don't have lambda, you just disregard the sigma 0, S0, and you have matrix without spin at all, and then it's just purely orthogonal. So, and the same you can do with the C symmetry. If you have two different charge conjugation symmetries, it will make exactly the same effect. It will break up your system into subsystems. Each of them will have fewer symmetries. And you can the more important, you can study them separately. They do not talk to each other. No need to average anything over all of them. You can average only over one of them.
These are even nicer in a sense.
Yeah. So finally, why do we need all these symmetries? What do they tell us? We need the symmetries because they define what kind of soft modes we have and what kind of interaction these soft modes also have. So, soft modes. As we discussed on the very, very, very first lecture, there is always one particular soft mode that exists in any system, which is called the diffusion. Diffusion is a ladder with two green functions, retarded, advanced, with impurities. And this thing always exists. Nothing can change it. Now imagine for a moment that your system has time reversal symmetry. So what we can do, we can apply time reversal operation to one of these green functions, only to the advanced one. And applying time reversal operation to the advanced function will flip the sign, the arrow. It will point in the opposite direction. So what you get after applying this operation is called the Cooperon. It's also retarded and advanced. Soft mode is a mode that can propagate to long distances in a disordered medium. A single electron cannot, it decays on the mean free path. This double electron thing diffuse and can propagate.
So in terms of our operator,
Which operator?
I mean we have some operator with which we act on the function, right?
No, I don't understand which operator
Well,
you're talking
in
about.
the very, very beginning when we defined a diffusion. Okay, well, first formulation model, right?
Right.
I mean, this model is a Hamiltonian.
Okay, diffusion is this object. This object is nice because it has a pole, it diverges at small q and omega.
Yes, and this object
This means that it is a soft mode, the divergent at small q and omega. This is another soft mode which also diverges at small q and omega, which exists if your system has time reversal symmetry. Diffusion exists always. This one exists only when your system has time reversal symmetry. And it's very easy to prove because you take the diffusion, you inverse time in one of these functions, and you get the Cooperon.
Why do we act with, why time reversal symmetry operator act with diffusion, why reverting just one of them? This is
You take the advanced green function. Advanced green function is energy minus Hamiltonian minus, it's advanced, yeah, minus I0 inverse. And you apply time reversal operation, namely, you replace Hamiltonian with H star because they are equal. You can also have this U matrices and then take them out. I don't care.
plus I0, probably plus I0.
Very good point. No. H is replaced with H star. Nothing else changed.
That would be the case if you had C.
H is replaced with H star. This is time reversal operation. H equals H star. So I use.
Okay, so you just use the symmetry, you don't
Yes,
act
I
with-
didn't do anything. I just used the symmetry. This equals this. Perfect. Another nice property of the Hamiltonian is that it's Hermitian. I mean, it equals to its Hermitian conjugate, which means energy minus H transposed minus I0. Yeah? This equals to this. Which also means energy minus H minus I0 minus 1 transposed. That's it. When you transpose, it flips the arrow. It just interchanges the two ends. You know, when you transpose a matrix, Mij transposed is Mji. And this is just a huge matrix, and the 2 points R and R prime are the matrix indices. So transposition means flip the indices.
But your statement that
Yeah.
But why work on the X with only one green function?
Yes, I said it in words. You apply time reversal only to advanced function.
Okay, that was the whole question.
I'm sorry. I should have probably repeated it a few times. I apply time reversal only to the advanced function, and I get a Cooperon. Now, I will,
Sorry, any reason for this, or just
sorry, reason for what?
why you apply only for one new function?
Because I have a diffusion and I want to make a new soft mode. If I apply it to both functions, I will get back the same diffusion. It's not interesting. That's why I apply it only to one function. Another thing that I can do, I can apply a C-symmetry only to advanced function. Remember, not to both, only to advanced function. What will happen? Question. So this is my retarded function, nothing happened, it's still the same. What will happen to the advanced function if I apply the C-symmetry? Sorry? Yes, right. It will actually both flip the sign, flip the arrow, and change to the retarded function. So what I will get, I believe, is two retarded functions pointing in the same direction.
Yeah, that's the flip response. So the flip of the arrow responds to the flip of the energy.
No, flip of the arrow is the transposition. Again, let's do the same trick here on the board.
But which is doing how can we see that if we have transposition, then arrow goes to different direction?
Because transposition interchanges the indices of the matrix. And arrow goes from the first index to the last index. Actually, from the last to the first, but doesn't matter. So now I will apply a C-symmetry, and I will say energy plus H star minus I0 inverse. And then do the same story. H star equals H transposed because it's a Hermitian operator. So I have energy plus H transpose minus I0 inverse. Right? And then I will take outside the minus sign and write energy minus H, minus energy minus H plus I0 inverse transposed. So when I take advanced function and I apply C-symmetry to it, I get minus, let me write it, it's the advanced function at energy E. What I get is minus retarded function at energy minus E transposed. So advanced function is changed to retarded function and is also transposed, and also energy is changed to minus energy, and also the overall sign is changed to minus, but who cares? Important is this I0, it was minus and it became plus. So this strange object is also called a couperon, but a very specific one. It's retarded couperon. Yeah, it's something we have never seen before. So, question to Dima personally. What will happen if I take a couperon, this one, the usual one, and apply a C-symmetry only to the advanced function? When I apply C-symmetry, it's written on that board. I change advanced to retarded, and I flip the arrow, so I will get something which contains two retarded functions, but opposite arrows. Why? This object has a strange name. It's called retarded diffusion. So whatever has arrows in the opposite directions is a diffuson in the same direction as the Couperon. These are usual ones, diffuson and Couperon, and these are some weird diffuson and weird Couperon because they have only retarded functions inside.
Usually we are arguing that such error Couperons and diffusons are zero because the poles in green function are on the same complex plane, but
This is correct only for systems with the simplest possible Hamiltonian, which is the scalar function of momentum called psi. These Hamiltonians do not have any C-symmetry. If you have a Hamiltonian like Bogolyubov, which has C-symmetry, it has H minus H in the diagonal, which means that in momentum space, it has always poles on both sides. Look, this is a tricky thing. When you say retarded or advanced, it means it has poles only in the upper half plane or in the lower half plane as a function of energy. So poles in energy. But then when you write the green function as energy minus psi plus I0 inverse, for example, this is retarded one, yeah? You can say that it also has a pole in a certain half plane for psi. But this is true only for the simplest case when you don't have any C-symmetry. If you do have a C-symmetry, instead of this psi, you will have something like a Bogolyubov Hamiltonian, which has both psi and minus psi. So it, as a function of psi, it always has poles in both half planes for retarded or for advanced. And that's the reason why you still can have the ladder with, say, two retarded functions. So retarded and advanced refers to the half plane in energy. It often translates to the half plane in psi, but only for this scalar type of the Hamiltonian. So last question to whoever is the first to answer. What will happen if I take this retarded Couperon and apply a T inversion, time reversal, to this lower retarded function? R diffusor, right. So by applying time reversal, I can go from here to here. Next question. What will happen if I take the original diffuson and apply a CT symmetry, the chiral symmetry, to the advanced function? Yes. If you apply CT symmetry, you go directly from here to here. What will happen if I take this RR Couperon and apply a CT symmetry? I will go to the other Couperon. I will not draw this arrow. So these four types of soft modes exhaust all possibilities. There are no other possible soft modes in a disordered system.
If you had just S symmetry, then you would have just two diffusors.
What is S symmetry?
Chiral.
CT.
Yeah.
Yeah, you will have only these two. Okay, so this is the comprehensive, complete list of all possible soft modes.
is it correct if we have two any type of symmetries, we have all three?
Sorry, which two type?
If we have any two types of symmetries,
In two
it
types.
automatically has the third one.
Yeah, we will discuss it in a minute. So these are all possible soft modes, and there are no others, which means that there is some finite number of possibilities for a disordered system. They are not infinite. So let's list all possibilities. Imagine our system. What can happen with the time reversal symmetry? There are only three options. T squared equals either +1 or -1 or 0. 0 means there is no time reversal symmetry. C symmetry squared equals either +1 or -1 or 0. 0 means there is no charge conjugation symmetry. If I count all possible options, how many? How many variants? 9. Yeah, 3 times 3 is 9 options. Whenever you have some time reversal symmetry, non-zero, and some charge conjugation symmetry, non-zero, you always also have a chiral symmetry because it's just the combination of the two. When you have time reversal symmetry but no charge conjugation symmetry, you do not have chiral symmetry. Yeah, because if you have a combination and one of them, you should also have the other one. And the same is true if you have charge conjugation but no time reversal symmetry. However, if you have no time reversal symmetry and no charge conjugation symmetry, if both symmetries are absent, this is one of these 9 options, yeah, when we take 0 and 0 from here. One of these 9 options actually splits into 2 because you either can have or not have the chiral symmetry. So it's possible to have chiral symmetry, the combination of C and T, without having C or T separately. That's almost obvious, right? So actually, there is plus one specific option, which is C squared is 0, T squared is 0, but the combination CT is present.
How can one check for sure that
Sorry?
How can one be sure that they have identified all the possible TCS symmetries of Hamiltonian?
Oh, well, it's a good question. I mean, I don't know.
So you can't be sure.
Actually, symmetries usually apply not to a single Hamiltonian, but to an ensemble when you have some random part. So symmetry should apply equally to all realizations. If you have just a single Hamiltonian, just a single matrix, by a proper choice of basis, you can make it diagonal. So it's nothing to talk about. Yeah, it splits into sectors which are exactly solved. But for an ensemble you can, and that might be a tricky thing. So there are in total 10 cases. 10, 9 plus 1 is 10, yeah? We now have 2 major discoveries that 3 times 3 is 9 and 9 plus 1 is 10. There are 10 possible cases which are also called 10 symmetry classes. Symmetry classes of disordered systems. And this is the full classification that we wanted to have. 10 symmetry classes in total cover all possibilities. Nothing else is possible. And for each of these 10 symmetry classes, there is a separate nonlinear sigma model. It is slightly different in every of these 10 cases. The sigma model that we studied on the previous lecture and before was the sigma model for the unitary class, which is one of these 10 options, namely the class where there is no time reversal symmetry, no charge conjugation symmetry, and also no CT symmetry. No symmetries at all. That's unitary class. It's one of the 10 options. So I believe I still do have a little time, and I will start doing this thing, but probably we will not finish it by today. What should I do to speed up this device? So symmetry classification, as I said, there are 10 options, and we can list all of them in a table which looks like this. T squared, C squared, and CT. Yeah, these are 3 columns. And we have the first case when there is no time reversal symmetry, no charge conjugation, no CT. This is called the unitary class, unitary symmetry class, and it has a common notation. It's called class A. Now, what do we know about this unitary class? A Hamiltonian is just any matrix. There are no symmetries, there are no restrictions. Any Hermitian matrix is a possible Hamiltonian. So, in the same table, I will draw a column which is called S, which is the exponent of IH. The exponent of the Hamiltonian. Hamiltonian is a huge matrix. S is also a huge matrix. And S has a name. It's called the scattering matrix or S matrix. No matter. It's just you take one matrix, exponentiate it, you get a different matrix. Question. If you take any Hermitian matrix and do this, what will be the result? It will be any unitary matrix. Yeah. That's why it's a unitary class. So S is a unitary matrix of size n. Small n is just the size of the original Hamiltonian, which can be 10 to 23. This is unitary class, and I will write the name unitary. Now the case number 2, which we also studied, when there is a time reversal symmetry and it squares to +1 and no other symmetries. This, for some reason, is called A1. When you have time reversal symmetry which squares to +1, by a proper choice of basis, you can bring the Hamiltonian to a symmetric form. The Hamiltonian is a symmetric matrix. It's a real symmetric matrix. Question. If you take a real symmetric matrix and do this, what do you get? No. Oh, that's a tricky question, actually. If you take a symmetric matrix and exponentiate it, H equals H transpose, yeah, is symmetric and real, and it equals H star. S equals exponent of IH. So, just by using this, you conclude that S is also symmetric. So, it's this. What happens here are all symmetric unitary matrices, but not real. I mean, they are complex, but they are symmetric. How can we think about this unitary matrix which is symmetric? This is a good question. Imagine an abstract unitary matrix, which is just big one without any restrictions. We can start with an arbitrary unitary matrix and construct a symmetric matrix out of it by doing the following thing, by taking U transposed and multiplying it with U itself. So both terms here are unitary, their product is unitary, and it's obviously symmetric. Next consideration. If you take two different unitary matrices, U1 and U2, and do the same thing with both of them. With U1, and with U2. Do you always get different results or not? Or let me ask it the following way. What should happen with these two unitary matrices such that this product is the same? If they are equal, it's the same, right?
If you multiply equal unitary matrix on orthogonal matrix, the result of such multiplication should be the same.
Yeah, actually the result will be the same if U1 and U2 are equal up to multiplication from the right by any orthogonal matrix. Yeah? U2 transposed U2 equals U1 transposed O transposed O U1. So as long as O is orthogonal, this is 1, you get U1 transposed U1. So we already saw this construction in a slightly different context before. So all the S matrices of this case can be described as arbitrary unitary matrices up to rotations from the right by orthogonal matrix. This is called a coset space, when you take the space of all unitary matrices and then you identify in a single entity all matrices that differ by this orthogonal transformation. And this is the wrong pen for this board. So this is called UN divided by ON. All unitary matrices of size n up to equivalence with respect to orthogonal rotations of the size n. This is called orthogonal class. AI, it's A1. It's A, and this is number 1 in Roman numerals. And that was A without any Roman numeral.
Is it possible to make one more column with the Hamiltonian?
But the symmetries are listed. Why do we need a Hamiltonian? So, third case, t squared equals -1 and no other symmetries. For historical reason, this case is called A2, Roman numeral 2. The Hamiltonian equals the transposed Hamiltonian up to rotation, which can be brought to the this is a bad one. So the Hamiltonian equals H star times this matrix 1 minus 1. Again, yeah, this should be inverse here. Or you can do the same, saying that it's H transpose and not H star because it's a Hermitian matrix. So, question. What can we say about the S matrix in this case? It was equal to S transposed, and that in this situation S equals S transpose. In this situation, if you do S transpose, it will again be equal to S up to the same thing, 1 minus 1 inverse 1 minus 1. So matrix S is any unitary matrix up to something. Let's take any unitary matrix and construct out of them the matrix that obeys this relation. How shall we do this? We transpose this matrix. We multiply it with 0, 1, minus 1, 0 from both sides. 0, 1, minus 1, 0, inverse. And we multiply it again by u. So now, if you transpose this matrix and apply this thing, you will get back the same. Actually, yeah.
U2n factor 2.
Sorry, which factor?
It's unitary group of size 2n factor 2 times u of
So,
n. No?
if you multiply the matrix U by any matrix from the left, by any matrix, let's call it A, then U transposed will be multiplied by A transposed. And then we insert these two matrices, 0, 1, minus 1, 0, inverse 0, 1, minus 1, 0. And if this product here, if A is such that this product is again 0, 1, minus 1, 0, then the matrix S does not change. So, S matrices that obey this identity are any unitary matrices up to multiplication with a matrix A that has this property, A transpose this times A equals this. In the previous case, this was a unit matrix, so A was just any orthogonal matrix. A transpose A equals 1. Now, these special matrices that it's called they preserve, these are matrices that preserve an antisymmetric form. If you have an antisymmetric quadratic form, A is a transformation that preserves its antisymmetric structure. This is called a name. In mathematics, it's called symplectic matrix. This is a symplectic form. This is a symplectic matrix. And the group of such matrices is called SP. And all possible S matrices here are UN divided by SPN, and this is called symplectic class. Yeah, I'm sorry if you didn't know what a symplectic matrix is. I can promise you these are all types of matrices. We will not have any others, just unitary, orthogonal, and symplectic. There will be no other types of matrices.
Correctly, that means exponent of Hamiltonians. Matrix exponent of the matrix.
Yeah.
It's like that's like the time evolution at 1.
So these are three options for the three symmetry classes, unitary, orthogonal, symplectic, which are also called A, A1, A2, which have some type of time reversal symmetry, but no other symmetries. And all these three cases have a Hamiltonian that, or exponent of the Hamiltonian that belongs to one of these. These are symmetric spaces. These cosets, when you have one group and you factorize it by a subgroup, you get a coset space which is a symmetric space, just like we had for Q matrix in the sigma model. But there are some different symmetric spaces. So we don't have too much time left, so I will bring it back later, hopefully. So let's consider the case when, first of all, when this board unfreezes, when there is no time reversal symmetry, no charge conjugation symmetry, but there is a CT symmetry. This case also has a name, and just by extrapolation you can guess the name. Wrong. It's called A3. Check means that this symmetry is present.
So it's not one.
It's present. Symmetry is not one. Symmetry is an operation, but It's either present or absent. So 0 means absent, check means present. What is this symmetry? What is this CT symmetry? Let me remind you. It's when the Hamiltonian changes sign, h equals minus h, with some unitary rotation. And by choosing a basis, this u can always be brought to the form 1 minus 1, to a diagonal form. Or, in other words, Hamiltonian, let me call this matrix sigma. The Hamiltonian equals minus sigma h sigma, which also means the Hamiltonian times sigma plus sigma times the Hamiltonian equals 0, because sigma squared equals 1. The Hamiltonian anti-commutes with the matrix sigma. And since it anti-commutes with the matrix sigma, the Hamiltonian can be written explicitly as a block matrix of this form, which has 0 blocks on the diagonal and some non-zero block on the off-diagonal in this basis where sigma is diagonal. And this is called chiral symmetry, and this is explicitly what is called a chiral Hamiltonian. So the question is, as usual, what happens if I take an exponent of such object? This is better. Okay, so this is the Hamiltonian anti-commutes with sigma. What happens with the exponent of this Hamiltonian? Just imagine, I take the exponent of the Hamiltonian, I multiply it with sigma from both sides. What happens? It changes into e to minus IH, right? Which means sigma S sigma equals S inverse. Which also means sigma S equals 1. Or sigma S squared equals 1. Actually, it's this thing is very similar to what we had in the sigma model. It's like a Q matrix. Something that squares to 1 and something that is parametrized by such a block of diagonal matrix exactly as we had with a W. It had B and B dagger. So in fact, the space of S matrices here is exactly that symmetric space that we earlier have seen in the sigma model. It's the space that is called like this, UN plus M divided by UN times UM. This is a most general form, N and M. It's when you have an equal number of columns. For example, this block is n times n, and this block is m times m. If this 1 and minus 1 have different size, then the block you have is a rectangular one, n times m, and then you have this space. If they're equal, it's just u to n by twice un, as we had it.
So it isn't necessary for n and m to be the same?
No. Chiral symmetry does not require this. Usually it happens that they're equal, but the most general form is like this. And this case has a name. Who can guess the name? This is called chiral unitary. Next case, do we still have time? Yeah, great. Next case, t squared equals plus 1, c squared equals plus 1, chiral symmetry is present. I will tell you the name, and all the rest you will guess by yourself. It's called chiral orthogonal. So, first question, what should I write here? What kind of space this S matrix belongs to? Just by analogy. This is chiral unitary. What should be chiral orthogonal? It's O n plus m divided by O n times O m. The same thing, but made of orthogonal matrices. Actually, the Hamiltonian, again, is this block of diagonal form, but now H is real. H transposed. So we take this Hamiltonian, and on top of it, on top of the chiral symmetry, we impose time reversal symmetry. And we just say this, if this is real, then this is chiral orthogonal case. And it has a name, as somebody already guessed, BD1. And the third case, -1, check. This is called chiral symplectic. Who will guess the space? Yes. SP n plus m divided by SP n SPM. And the name, again, obvious, it's C2. So we have three options. Unitary orthogonal symplectic with only time reversal symmetry, and analogous three options when we included chiral symmetry and then take these three. And there are 4 cases left. It should be 10 in total. We have 6. There are 4 left, and I will go a little bit faster because I have only 1 minute. So 0 plus 1, 0, or 0 minus 1, 0. Let's take the first one. The only symmetry of the Hamiltonian is the charge conjugation. So the Hamiltonian is, in certain bases, antisymmetric. It changes sign when you transpose it. Question: what is the exponent of such a matrix? It's antisymmetric matrix. Exponent of an antisymmetric matrix. Who knows? It's orthogonal, right? That's it. It's just an orthogonal matrix. If you multiply this with complex conjugate with a minus, with a transposed one, transposed gets minus, so you get 1, so it's orthogonal. And this one means when you transpose and multiply with these strange matrices, it changes sign. This is, I will not bother you, this is just symplectic. No. The names of these two things are, I always mix them up. The names are D and C, exactly. And there are 2 others left, which are -1 plus 1, check, +1, -1, check. And I will not derive anything here, I will just tell you. This one is orthogonal divided by unitary, and this one is orthogonal. It should better write 2n, orthogonal of 2n divided by symplectic. Oh, sorry, symplectic divided by unitary. What am I saying? Symplectic divided by unitary. I hope I did not mix them up. These classes also have names. This one, for simplicity, is called D3, and this one is C1. These two cases combined, C and D, sometimes are called superconducting unitary because they don't have time reversal symmetry. This is superconducting symplectic. And the last one is superconducting orthogonal. And I hope I did it correctly. Wait, please. Yeah, I did it correctly. Yes, just like it's written. This one is orthogonal, this one is not. What's your problem? No, look, orthogonal is whenever t squared is plus 1. Symplectic is whenever t squared is minus 1. But these actually, for cases, these are not standard names. So for chiral and usual, they're standard names. These I just invented yesterday. Yes. This is a classification for Hamiltonians which have some randomness.
So without randomness, no.
Without randomness, your Hamiltonian has too many symmetries to be classified. Okay, so let me bring this whole table on a single screen, like this. Yeah. Just a brief mention of what these strange letters mean. This is the classification developed 100 years ago by a mathematician, Élie Cartan, for symmetric spaces. This is the exhaustive list of all possible symmetric spaces. And these are the names for these spaces according to Cartan. Cartan is a name. And it's very simple. Whenever you have unitary something, you have the letter A. Whenever you have orthogonal something, you have B or D. And whenever you have symplectic something, you have C. I mean, in the numerator. And then, depending on what you divide it with, you have numbers 1, 2, 3, whatever. So there is some system. I mean, it's not exhaustive. I have no idea why D3 exists, but D1 and D2 do not. I don't know.
I doubt Cartan was looking at the unitary evolution.
No, Cartan was working on symmetric spaces. So he had a classification first of semi-simple Lie algebras, then Lie groups, and then these are generalizations of the Lie groups, which are cosets built on Lie groups. And for Lie groups, it's easy. The classification is A, B, C, D, just for letters, which is unitary, symplectic, and B and D is orthogonal of even or odd size. B is odd size, D is even size. And then when you divide it by something, you add some numbers.
Also to other stuff, not just these.
Yeah, actually for groups, for these cases, U, O, S, P, it's just A, C, and D. Well, this D actually, depending on whether n is even or odd, can also be. I mean, you can also write it as BD sometimes.
I was always confused with these names for these systems.
So once again, the letter tells you what is in the numerator, and the number tells you whether it should be divided by something or not. So that's it for today, and next time we will start with this table and we'll add a few more columns to it.